What is SAGA? SAGA is the short name for System for Automated Geoscientific Analysis. It's a GIS, a lightweight GIS software, and its main objective was to be a system that is designed for an easy and very effective implementation of spatial algorithms. So it should be possible to extend the system very easy. And in the meantime, SAGA offers a large set of geoscientific methods. It has a user interface with many visualization options. And currently it runs under Windows and Linux. And it's a free open source software. So the development of SAGA is mainly driven by the University of Hamburg, the Physical Geography of Hamburg, and especially Olaf Conrad, who is the inventor of SAGA. And in the meantime, there have been several contributions from other people. It's just a list of some inputs which has been compiled by Olaf. So let's have a look at the architecture of SAGA. It's a very modular system. Its foundation is where's my mouse pointer? The application programming interface. This interface provides methods for programming things, computational methods. It provides constructs for data objects, and yeah, it has a growing set of classes which you can use to program so-called modules. Modules are organized in module libraries. They sit on top of this programming interface, and these modules are simply dynamic link libraries, so you don't have to change anything at the foundation of SAGA. You can simply extend the system by providing new libraries which are loaded at runtime. So these module libraries are actually the containers of the scientific methods. As well as the module libraries, we have a graphical user interface which allows to manage the modules, the data, which allows to load data, to execute modules. And yeah, it's one of the possible interfaces to SAGA. We also have a command line and other things. So this is just a small example how a SAGA module looks like in source code, just to show you how simple it is. It's written in C++, but you actually don't need to have much knowledge of this programming language to implement methods. So this is the constructor of a module class, a class which computes an analytical hill shading. And you can see you simply can add parameters. In this case, we add two grids, which then show up in the GUI as selection. One is an input grid, parameter input. It's the elevation data set. And the other one is an output grid, the analytical hill shading result. And we have some parameters which are not listed here. And then you have, besides the constructor, you have a method, the onExecute method, which is called once you execute the module, once you run it. And in this case, you can simply get your grids as data sets. And then you run through the raster row by row and try to calculate its gradients, slope and aspect. If it's possible to calculate it for a cell, then if it's not possible, then you set the cell to no data. Otherwise, you can simply calculate the shading and write the result back to the grid cell. So this is more or less the complete code to run or compute a hill shading grid. Okay, and this makes it really easy to extend SAGA for your needs.
So this is not a C++ syntax,
This is C++.
This is C++.
Yes, but you see that you have many SAGA classes which facilitate the implementation. That's why I meant you don't really need to have an in-depth knowledge of C++. It will help you implementing your methods if you have it, but all the interaction with data objects and stuff like that is very comfortable because the RPE provides you methods like getting gradients or writing data. Okay. So in the meantime, we have 62 libraries with over 450 modules. It's clear that not all modules are highly sophisticated analysis or modeling tools. Some perform really simple operations, typical GIS operations. But there are also some really interesting modules which you will not find in any other GIS package, especially for terrain analysis. So we have for sure a lot of modules for data import and export. We have cartographic projections and georeferencing by linking to the Proj4 library. We have a lot of basic raster tools like buffering, contour line creation, and stuff like that. In the meantime, we have a growing set of vector tools. SAGA started mainly as a raster GIS, but now we also have quite a lot of vector tools. We have a big set of terrain analysis methods for hydrological or other analysis. This is where SAGA actually started in terrain analysis. And we have some modules for image analysis. This is also extended from version to version. The next version, for example, will include a support vector machine classification algorithm and stuff like that. Okay, today we can only touch a very small sample set of these modules, but I think you will have, or you can explore it yourself then. So this is just a small overview about the GUI. I will show some other slides afterwards. Just to show you what you can visualize with SAGA. The most important for sure is the map view, where you can compose maps, but you can also show histograms, you can create scatter plots and stuff like that. I will say some things about the organization of the GUI later. Okay, besides the graphical user interface, SAGA has also a command line interface, command line interpreter, which is not, you may say that user-friendly, but which allows you to automate your tasks.
We actually, most of people here, they are our users, so actually the way we use SAGA is mainly with the R SAGA package, which actually makes it quite smooth. And I think Alexander Brenning, who made the R SAGA package, made lots of wrapper functions, so you can like very quickly call something.
Okay. Yeah, it's very nice. We use it too. It's just that we use the GUI for visualization, but all power tasks are done by scripting. And just a little tip, in case you are more used to GUI, you can, in the GUI, you can do a right click on a module and then pops up a menu where an option is provided to create a script command line file. So this will provide you something like a template, which you just have to change to match your paths and data and stuff like that. On the right, you see a small example how such a batch script might look like. It's actually very simple. You call SAGA command, you call the module library name, then you get a list of modules. You can call them by name or by number. In this case, the analytical hill shading is called, and then you have to provide the parameters as with every other command line interpreter. Okay. It's also possible to use the Swig compiler to expose the SAGA API to various other scripting programming languages. Most popular is, I think, Python, which is used a lot, and also the AirSAGA interface could make use of the API, but I don't think it is done. It's a separate package. So, yeah, Olaf has compiled here some impressions of last meetings and stuff like that. In case you need further information, you can go to the homepage, saga-gis.org, where you get basic information and a lot of references. The project itself is hosted as SourceForge, where we have something like a wiki, bug tracker, feature tracker, a user forum, and stuff like that. So there you also find links to guides and tutorials and stuff like that. Okay, so let's have a very quick look at the graphical user interface before we actually start with the first exercises. Some basic concepts. First of all, there is one thing which is a little bit different to other graphical user interfaces in SAGA. You have common elements like menu bar, toolbar, data views, status bar, and then you have three windows which are interacting. The workspace window and the object properties window on the right. The workspace window itself has three tabs: modules, data, and maps. And the special, or the thing which is special about SAGA is now that depending on which tab you select in the workspace on the left, it's modules, data, or maps, the object properties on the right are changing. You will always see the settings of the tab that you choose in the workspace. This makes it possible to expose you almost all parameters you need to change in a very fast way. You don't have to go over menus or stuff like that. But you have to keep in mind, once you like to change the settings of a data set, change to the data tab, and then the object properties will change to this data set, and you can change the values. So yeah, you see that you have, in the case of modules, you will get the module settings, that is the module parameters, input, outputs. You can get a description in the object properties. Or in the case of data, you have settings like no data values, color palette information, and stuff like that. And in the maps, you have the possibility to arrange your maps, your layers, and stuff like that. Okay, so when we will start SAGA the first time, it will try to load all available module libraries directly, automatically. In case you are missing some libraries, or you have some libraries installed in another path, you can use the menu to load a library. The modules can be called via a menu or from the workspace. Today we will mostly use the workspace because it's easier to show. And yeah, then you have to provide data, parameters, then you can execute it, and then you will get a message printed if it was successful or not. You have typical navigation tools you know it from other GIS. I think it is more or less self-explanatory, so we will have a look later at these tools. And yeah, we will learn about these things too once we do the first exercise, how to show a data set. You can rearrange data sets in the map tab by simply moving them around, the layers, to arrange a map and stuff like that. Just a quick overview before we actually start. The display options for vector data, you can use very different colorization options. The same for raster data. I step one forward, where you can have gradiated colors, lookup tables, very powerful palette editor. You can use the histogram to stretch your data to specific data ranges. For example, if you like to visualize more detail, in this example you don't see very much detail in the lower part of this DEM. So you can limit the value range to get more detail simply by providing the values or by selecting the appropriate part in the histogram, or you can even scale it logarithmic to get even more detailed, for example. One special thing about raster data, or grids, how we call it in SAGA, is, so I step back, that, or how should I start? A grid is actually defined, completely defined by an offset position, the lower left corner, by a cell size, and by the number of rows and columns. This is what we call a grid system in SAGA, because you can describe the location and resolution of a raster by these three parameters. And in SAGA, all data is organized in these grid systems. So if you have data with, for example, different grid resolutions, cell sizes, then it will get loaded into different grid systems. And unlike to other GIS, like for example ArcGIS, SAGA does not automatically resample your data. So in case you would like to compute something with grids from different grid systems, you have to do it yourself to resample this data. This has the advantage that you know which resampling method is used to match your data, and it's not done automatically in the background. And sometimes it's a little bit of a hassle because you have to do it on your own, but you have the full control. So this is, I think it's more important.
It's a bit sensitive. The grid system, the sensitive, like if you have basically the same grid system, but it's been rounded with different decimal places, it's not going to recognize it, the same grid system.
It's sometimes a problem.
Yeah, because I saw all these things from R.
Yeah.
But I think it's a bug.
It's mostly if you have let long coordinates with very many.
But also with the metric coordinates.
Okay.
Just because I have a few more digits or something, the numbers are exactly the same. SAGA doesn't recognize it as the same grid system.
I know it too. So the most easiest way to fix this is to simply open the header file. Yeah. SAGA has a grid in SAGA has an ASCII header. This is what you see here. It's just a small text file, and it has a binary part. And in case you encounter this problem, the best way is to just reduce the number of decimal precision in the header by editing the ASCII and reload the grid. Okay, so this was just a quick introduction, and now I think we can start. The first steps. We actually, where is it? let's go back here. Actually, we have already done the first steps. I just provided some information how to install SAGA. But as you all have it installed already, we can skip it, I think. You can download it and just have to decide, for Windows you have to decide which operating system, 32 or 64-bit. And then you just extract it and you can run it. So it's very nice. It's more or less a stickware. You can start it from your memory stick. So you don't need any writes on your computer to run it. And you can see you have a SAGA GUI exe and you have a SAGA command exe. This is the command line one. Okay, so I think the memory stick. Yeah, okay. Because I think you are still missing the demo data. Do you have it? Ah, okay, sorry. Okay. For Linux or FreeBSD, there are some binary packages provided, but most likely you will need to compile it from source. It's described in the wiki if you like to do that. Okay, so let's have a look at the supported data formats. SAGA supports some native formats that are tables, that are tab delimited text files or DBF files, then shape files, S3 shape files, SAGA grids, it's an own format, and since I think 3 years now we have implemented a further data type which we will use today too, point clouds, SAGA point clouds. So most likely you will get data from other sources, and for this we have 10 import-export module libraries with almost 70 modules to import or export to different formats. The most powerful one is for sure the GDAL OGR module, supporting a great number of formats. And yeah, since GDAL version 1.71, we also have a SAGA grid driver, so you can access SAGA grids from other software which is using GDAL 2. For example, in the meantime, even ArcGIS or yeah, most open source software products running GDAL OGR like QGIS or stuff like that. And we have, since we implemented point clouds, we have a module for importing LIS files. LIS files are a common format for LiDAR data, so we will use it today to get some LiDAR data into SAGA. Okay, so let's start. I provided you a simple SRTM geotiff file in the data folder, and so I will need to start my SAGA version. You will see some differences as I'm currently working on Linux, so the GUI is a little bit different, but it should be no problem. And I'm working with a development version. It's not very stable, so don't care if I get some problems. You should not have any problems. So once you have started SAGA, you will see almost this setting of the GUI. Most likely you will have a fourth window, a data source browser, which we will not need today. You just can close it by clicking on it. One thing which we might change at first is when you go to the modules tab, to module libraries, then you have an option. You have the general settings for module libraries. And there's a beep when finished option. So if we don't want to have too much sound in here, you should disable it. Otherwise, we will have some bloop every time a SAGA module is finished. So you can disable it, and all changes that are done in a settings tab have to be applied. So don't forget to apply the changes. So yeah, we will not hear all these sounds.
How do I open a new section? Because when I open the last project,
a new section?
When I start, then the last project I have, the last one.
How you get this window back, or what do you mean?
They started, this is the last map. I want to open without map, without any map.
Ah, you want to start with a clean
empty one,
project.
yeah.
The easiest way to start with a clean project is to go to use File, and then Project, New Project. This will ask you to save unsaved datasets, and then will clean the graphical user interface, and you can start with an empty project. Okay, so let's start with the import. And here we can use the import-export GLOGR module. Simply open it, and then choose import raster. And then you can select a file by simply clicking right to it. Then you get these ellipsis button. And once you click on it, a normal file browser will open, and you can go to the folder with the data and select the TIFF file. So I have to move here, data. Okay, then you have to apply and execute the module. And this should import you the data. So, and when you change to the data tab, then you will see a new grid listed. You will see the grid system. So you can see it here. It's again, as I explained, it's sorted by grid system. We have a cell size, we have the rows and columns and rows, and we have the lower left coordinate. So this is how the data is organized. Okay, to visualize it in a map view, you can simply double click on the data set, or you can use the right mouse button, which will show you some other options. For example, add to map. I think in your version it might be called show. Just double click on it, and then a new map view opens and will show you this data set. It's colored in grayscale. You can have a look at the settings on the right. If you scroll down to the color palette, you see that it is of type graduated colors and that it has a grayscale color palette applied.
Because I have a problem with your...
Yeah, can I have a look? So you executed it? Yeah, you already executed it. It succeeded, yes. Yeah. So you can do cancel. Yeah. And then you change to the data tab, and now you have a new data set, and you do just a double click, double left click.
Oh, okay.
Yeah, okay. So you can close this one because we will not use it today. Okay. So
it's another way to import the data?
it's a way to load data and stuff like that. It's a little file explorer, actually. Okay, so the first thing will be to create, to use another palette, the SAGA default palette, to change from grayscale to the SAGA default palette. And this is simply done by opening up the color palette editor. Once you see the settings and you click into the field of the colors, have you copied the data? Is it working? Okay. So you can just click in the field and then on the ellipsis button, and this will open up the color palette editor for graduated colors. I show it again. Just click in the field of the colors and
Connections.
okay.
Wenn wir schnell sind und schnell wieder ins Internet kommen, geht's.
Where is it again? Wir haben alles aufgehört. Okay. So the color palette editor is very nice and powerful. It's the RGB components and the brightness, and on the bottom you see the final palette. And one way would be to simply edit this by dragging lines and altering color components or clicking into it. So you can very easily create smooth palettes from with this, for example, for terrain visualization from green to brown to white. But we will use the preset now. Just click on preset, and then you get a list of gradiated color palettes, and we will use the default one for now. So this is just a palette ranging from blue to red and showing a lot of detail. Once you have selected it, you can press OK. And then nothing has changed because we still need to apply our changes. And once you apply it, you will have your data set colored with the new palette. Now I told you about histograms. You can open up the histogram of this file by a right click and then select histogram. So you see the distribution of values. In my case, I cannot make it floating, and on Windows that's not possible. On Linux, I have to switch, but you have it as a floating window, and you can simply use the left mouse button to select a color range and to stretch to these color range. So you can provide select which elevation values are shown with a greater detail. And once you would like to stretch back to full extent, you use the right mouse button. With the left mouse button, you zoom in, and with the right one, you zoom to full extent of the data set and get back the colorization used before. Not exactly used before, because once you do a right click on the data set, you can see in classification. In this case, now we rescaled the data to use the minimum and maximum values. In order to exclude some outliers, by default, a data set is scaled to its standard deviation of 2. So if you like to get it back to the original looking, just select classification and set range to standard deviation of 2. then it looks as before. Another nice thing in SAGA is that you can enable show cell values in the settings. You just activate it and press apply. Then you will see nothing, but once you zoom in with the left mouse button, you can drag a window. Once you zoom far enough in, you will see that the elevation values show up. So it's very handy in case you like to investigate some values in a grid. For sure, you get them by mouse over too. You see it in the bottom line, the set value. But in case, for example, you have categorical data or stuff like that, it's very nice to visualize the cell values too. Once you zoom out again with the right mouse button. Excuse me. The right mouse button. Just a right click in the map with the zoom tool will zoom out. Or you can use these buttons like zoom to full extent, for example. Then you get back to full extent. So let's have a look at the analytical hill shading module. It's in the, you have to scroll down in the modules tab. And there's a module library called Terrain Analysis Lighting Visibility. And then if you open it, then you see that there's the analytical hill shading module. Once you select it, you get its settings displayed in the object properties window. And as I said, that you will not be able to compute on grids which are in different grid systems. The first thing is that you have to select a grid system. So in our case, we only have a single grid system selected. And once you have specified the grid system and you click into the elevation data set parameter, you will get all data sets listed in this grid system. So we can select our SRTM dataset. Yeah, and then we have an output dataset which will be created. We could also overwrite an existing dataset, but in our case, we like to create a new one. And we have some other parameters, the typical parameters azimut and declination of the light source for lightning. So now we will use the typical settings from Northwest. We have the possibility to exaggerate the digital elevation model before we apply the computation. This is exaggerated per default by a value of 4 to get a better impact. And we have a lot of shading methods. So once you click into this parameter, you get a selection box. And what you know from analytical hill shadings is the standard settings. It's just an analytical shading. But you can also, for example, do a ray tracing, which will calculate real shadows. So a large object or a large ridge will really throw a shadow depending on its height. But for now, we will use the standard setting. One thing to these arrows, arrows pointing to the right are input data sets, and arrows pointing to the left are output data sets. 2 arrows means that this is a mandatory data set. That is, you must specify it. If we had some parameters with 1 arrow, then it's an optional data set which you can use, but which must not be used. So once we have specified these parameters, we can execute the module, and then changed the data tab, and here we have another data set now. And by doing a double click on it, we are now asked if we like to add it to the existing map or if we would like to add it to a new map. We like to add it to the existing map. So we select it and press OK. And then it is stacked on top of the other layer. You can see this by changing to the Maps tab, where you have now one map. And you see we have two layers, the analytical hill shading on top of the SRTM dataset. So if you change back to the Data tab and click on the analytical hill shading, you will get its settings. And then you can change the transparency parameter. Just click into it and change it, for example, to 40%. This will make this layer transparent. And then apply the changes. And then we have a nice hill-shaded colored DEM, which provides much more detail than the elevation data set itself. Okay, so the last thing I would like to show with this data set regarding the visualization options is that every map view which you compose can be viewed in 3D. You can simply arrange your map, making a layout with different layers. And then you can use this 3D button on top to open up a 3D viewer. And in order to display it in 3D, we need to specify a data set which will give us the height information. So in our case, we again select our grid system, and then we use the SRTM as elevation data set. You can leave almost all other parameters to their defaults for now, but when you scroll down, you have a resolution parameter. This is just how nice it is rendered in the 3D view. So we will increase it to 1000, for example, to have more detail
No,
in
it
3D.
is too much because it takes a lot of RAM and processing power.
I think 1000 should be possible. And once you click on OK, you will have a 3D view, and then you have a lot of buttons to navigate, but you can also use the mouse, the left mouse button. If you click and hold it, then you can rotate the 3D view. You can use the mouse wheel to zoom in and out.
Not bad for an open source software, huh? Which is 20 megabytes in total.
Yeah. It's nice, yeah.
Can you produce like a small video?
Yeah,
Application?
you can do this by simply selecting a position, and then you see from the 3D menu which popped up that you have a sequencer, and the key in the brackets is the shortcut. So you just remember A for adding positions and P for play. So you can simply select the starting position, use the A key to store a position, then you go on, select the next position, press the A key, move on, and so on, until you have done a few positions. And once you press the P key, it is played. You can export it as images, so you can make a small video, you can play it as loop.
Impress people.
Yeah, it's always nice to visualize it like that. You can also change some parameters, like for example, if you open up the sequencer, you can, first of all, you can play and save as images, which will render it as single images, which you can use to make a movie. And you can also edit the positions. That is, that you get a table where you have every position listed. And for example, the possibility to control the speed of the flight is the last parameter steps to new position. So you can simply add more steps to make it slow, and you can use fewer steps to make it speed up. So you have some, let's say, basic limited possibilities to control the movement. Okay, so these are some basic visualization options. You can also view in, I forgot, you can view in anaglyph with red-green or red-blue glasses. Just simply click on it and you can have it in 3D, rendered in 3D. You can exaggerate your data and stuff like that. You can explore this by yourself, I think. Okay. So there are a lot more possibilities for sure to visualize this data. But before we have a break, I don't know, at 10:30?
For 15 more minutes.
Yeah, okay, that's nice, because I would like to show you some basic terrain analysis possibilities. So you can start to explore that on yourselves then. So we moved on here to all these stuff. We had done this, so here we are. There's one module which is actually a meta module coupling several other modules, which calculates a selection of basic parameters that you can derive from a digital terrain model. It's using more or less standard settings, and if you want to know which are these settings, then you would have to have a look at the source code. I can show you if you're interested. I've listed here all module libraries and the corresponding modules that are used or coupled in this meta module. So you can see, first of all, we have to do some pre-processing. We will use a module called sync removal, which removes sinks in the digital elevation model. So we get a hydrological sound, DTM, which we can use for flow path analysis and stuff like that. Then the module calculates an analytical hill shading, which we have done already. Then there will be a module called that calculates slope and aspect. It will actually call twice, because in between the DTM will be smoothed a little bit to get nicer results for profile and plan curvature. So we will first calculate slope aspect and then profile and plan curvature. And then there are some more specific modules called the convergence index, showing if the flow is diverging or concentrating for erosion studies, for example. We will calculate the catchment area. We will calculate flow width and specific catchment area, the topographic wetness index, you know, maybe from the top model of Bevan and Kirkby. The LS factor, the slope length slope factor of the USLE, soil erosion equation. And then we will have finally called two modules. One is deriving the channel network and the drainage basins, and the other is calculating a vertical distance to this channel network. We will have a look at the results soon. So the module is found in the terrain analysis compound analysis library. It's called basic terrain analysis. And it has a lot of parameters because it's simply coupling all these modules. It's more or less, instead of scripting this, it is very easy to program such meta modules in SAGA. It's done in C++, but you just provide calls to each module and provide the parameters you would like to use. So in our case, we simply select the grid system again and provide our elevation data set as RTM as input. That would be enough, but we already have an analytical hill shading grid, so we could specify it here, so we don't create another one, we simply overwrite it. We overwrite the existing one.
It will be created again, just over the other one.
It will be just deleting the old one, and
Yeah,
it will be.
Do it again,
yeah, it will do it again. We cannot stop it from calculating it, so maybe, so I think it's better we overwrite it instead of having two identical data sets. Okay, and then you see all these grids that will be created, and you can see that we also will get two shapefiles, the channel network and the drainage basins. So simply execute it, and then you see the progress bar running. You can have a look at the progress report here, what is going on. There's always a short message, which module is called and which state of the art. And then it should be finished.
If you take a look at the data set, the data names are already there, even though he hasn't created yet. The first thing that he does is create names.
Yeah, these data sets are created first, initialized,
Yeah.
and then they are filled with with data once they are computed. But this is something which you don't have to care as a programmer, because the RPE will do this. This is why they are created, because they are specified as output parameters, and before the actual computation starts, the API will simply create these data sets, provide it to the GUI, and then they can be used for computation. But this is something, it's an automatism, which you don't need to handle yourself. So, okay, so you should get a lot of new data sets. And then, yeah, let's have a look at one. We know the analytical hill shading. Just have a look at the slope data set by doing a double click on it and adding it to the existing map, for example. So you will see the slope. You can see when you move the mouse over the grid, then you have reported the coordinates and the set value. The set value is the slope in degree. So we have very low slope values down in the in-valley and higher slopes in the mountains. But you have to be careful, because this is something which is special about SAGA too. Aspect and slope are actually calculated in radians, not in degree. But to get it reported in degree, these grids use a set factor, which is simply 180 degree divided by p to convert between radians and degree. So this set factor is used or is multiplied to report you the values in degree. If you change it to 1, which is the default setting for all grids, then you will report the actual values, and you will see that you have now 0.5 and stuff like that. So in case you do a reclassification of this grid, or you like to compute with this grid in the grid calculator, be aware that it is actually radians. And otherwise you will create a lookup table, for example, for slope classes 0 to 5 degree, 5 to 10 degree, and you will wonder why it is not working, because the actual values are stored in radians. So the simplest way is to use the grid calculator and multiply the grid with this set factor. Then the actual values in the grid will be in degree 2. But yeah, almost all modules that are working with such grids like slope and aspect expect it in radians. So SAGA just uses this set factor for converting it to degree.
Is there a place where we can get this information? If we run a module that we don't know, is there some documentation?
Yeah, we have some guides, but they have many pages, so you will have to have a look to find it. There are some tutorials which mention this, but that's why I mention it, because it's a typical mistake every new SAGA user is making, calculating slope and then not being able to use it actually. Okay, so next one is aspect. We can simply click it through. It's as you would expect it. Then we have plan curvature or horizontal curvature, showing us ridges and stuff like that. Then we have the profile or vertical curvature, showing us valleys and things like that. Then we have the convergence index, which shows us flow convergence. It's showing us the ridges in brown and the valleys in blue. Then we have the catchment area, which is actually a flow accumulation grid. And here you can see, if you scroll down to the settings, you could enhance this by switching to a logarithmic scaling. You will need to change it, for example, to 100, I think. Then you get more detail. So you can see the more detail in the lower values. So you can slowly increase this stretch factor and get more and more detail in these areas where the catchment area is low. So it's a very nice feature. You see that it is calculated by a multiple flow direction algorithm. That is, you have smooth transitions. You don't have a single flow directions, which will get you many parallel flow paths and stuff like that. Then we have the wetness index, which is a combination of catchment area and slope. We have the LS factor, showing us the slope length. And then we have two grids, which are quite interesting. One is showing the altitude of a cell above the channel network. That is more or less how much potential energy is available to the erosion basis. And the complementary grid is how is it called exactly? I have to scroll. Channel network base elevation, base level, which is something like an estimation of groundwater height, because it's interpolated from channel network to channel network, from stream to stream, trying to follow something like a groundwater table. It's not very useful here with this steep terrain. But in case of you have not that steep terrain, it's providing quite interesting results. Okay, so and finally we got two new data sets which are listed under shapes, organized in line and polygon shapefiles. You can maybe first use the Nash basin, double click on it and add it to the map. Then you see Grenache basins. We can, for example, change the colorization. For example, we have here now everything colored as single symbol. Simply click on it and use gradiated colors. And then go to the color palette, which is now 10 colors. Click on it, open the color palette editor. Maybe increase the count by clicking on count to 20 colors. And then you can use the random button to colorize by random. So each basin will get a random color. Okay, and apply it. And then you will have a map where you can distinguish each basin. Yes, and finally, we have the channel network, which you can add to. It's a line shape file showing you the channel network. So in most cases, it will be better that you don't run this module, which is doing a lot of parameter settings automatically. But it would be better to run each module individually and adjust its parameters. Because you see here we have some problems. We don't have some basins. And this is because the first step didn't run smoothly in automatic mode. We have not filled all sinks. So the flow path is disrupted and we cannot continue to derive the channel network. So this was just a good chance to show you some data sets in a very short time. But you should have a look at the module libraries. For example, the pre-processing library contains a lot of other sink filling methods. I have had a time where I had a little bit of a spleen to implement methods that were published by that time. So we can see the pre-processing includes, I think it's 7 modules for removing sinks, 7 different methods. Some ones specially optimized, for example, this one for very large data sets. So they don't use much memory, but yeah, you can have a more detailed look. In any case, if you would like to have more information about a module, you can click on it and then you click on the description tab and you will get some information. For example, in this case, it's what is done by the module and a reference to the paper which describes the algorithm. Okay.
And the code can be seen or not?
Yeah, for sure. You can have a look at it. It's simply, one way is to browse it in the web interface at SourceForge, or you download it. I can show you, for example, and maybe we have a look at this one, which I showed you. It's simply modules terrain analysis preprocessor, and there we have all sources, and the one we had a look at was this one. So where is it? Here. So this is how every SAGA module looks like. It has some licensing information. then it has some description. And then what I have showed you in the introduction, you have to add some parameters. It's very easy. Maybe switch off the line ending. So in this case, we have parameter input, a grid, and a result as output. And we have one parameter, a value, a minimum slope that should be maintained. Then we have the onExecute function, simply getting these data sets as objects, setting names or stuff like that. And then it, in this case, it's a highly optimized code, but you just move through the grid and calculate it. But you can see the source code for every module. That's a nice thing of open source, because you can change it, you can adapt it to your needs, and you can have a detailed look how it is really working. You can bug fix it in case you discover problems and stuff like that. Yeah.
Damage.
For example, you can damage it too, yes. But yeah.
But the development of the code, I mean, the SAGA core code, it's still by Olaf, right? I mean,
Yes, he's doing.
So one person maintain.
Yeah, and in the meantime, we do a lot of things too, but he's actually the main contributor still.
Now, I mean, I'm leading two software packages, but we do it via RForge, so I have a community and they can all commit, so the code is being merged.
Yeah, we are looking for contributors, because it would be easy to allow them S4N write access.
You don't have to even allow write access to all scripts. You can say, these are the scripts, and you can assign people to maintain specific. For example, you could maintain the sync filling algorithms.
Yeah.
So that's how, like, with our approach things function.
Yeah. Yeah, we actually are we are less people than we could be. When I look at the downloads, in the meantime, we have over 1,000 downloads a week. So it seems like many people are using it, but we don't get much feedback on regarding patches or codes or new modules. But we try to incorporate it in case we get it. So, yeah.
All this file data.
Excuse me, it's a full screen. So first of all, I would like to give a short introduction to LiDAR, because I think it's a very new thing and maybe not all of you know about it. LiDAR is the abbreviation for light detection and ranging. And the scanning mechanism is the following. We have a scanner measurement unit sending out a light pulse, which is reflected by a mirror, and this mirror is moving. So the beam is moving. You see it here. The beam is moving through the room, and each reflection is recorded as a point, simply X, Y, Z coordinate. So the actual measurement is the measurement of transit time of the light beam. And this allows us to calculate the range. And together with the measurement of the scan angle, we can get coordinates. In case of an airborne laser scanning, which is the most conventional method for deriving topographic data sets, the scanner is mounted on a plane, scanning the ground. And besides the laser scanner, it is necessary to have a high precision GPS, which records the location of the plane or actually of the scanner. And we need an inertial measurement unit, IMU, which also records the movement of the plane, roll, pitch, yaw. And from these coordinates, we always know the exact orientation of the laser beam. And with all these coordinates, angles, and stuff like that, it's possible to calculate X, Y, Z coordinates. You see that all these measurements must have a very high precision, and that's actually still the problem, which is limiting the actual precision of the coordinates. Because once you have a bad GPS signal, you will not have very accurate plane positions, and then you get errors of the point locations. So with evolving technology, it's getting better and better, but this is the limiting factor. And actually we have precisions of about a few centimeters, horizontal and vertical. So how is it done? It's simply the range is calculated from the speed of light and the travel time divided by 2. The laser beam is shot, and we measure the time until it comes back to the sensor. And about the light speed, we can calculate its travel time. And a very special thing about LiDAR is that the laser beam divides up with travel. Like if you have a handheld and move along, you get a footprint that is getting larger and larger. The LiDAR beam gets diverged more and more, so that we get a footprint of about 1 meter when we touch the ground. It's getting bigger and bigger, and then we have a light of about 1 meter in diameter footprint. So a part of this light will be reflected on the top of every object which is standing on the Earth's surface, for example, a building or a tree. But some of the light of this footprint will also penetrate the vegetation because there are gaps in it and stuff like that. And so you hopefully you can get more reflections even within the tree, but hopefully you get a last reflection from ground. And this is something very special about LiDAR, because this allows to create high-resolution digital terrain models under vegetation, which you cannot do with classical photogrammetry. You have always the vegetation height, and then you must make some assumptions how high are your trees to remove them. So as classical photogrammetry cannot provide these points, true ground points. So this is a really nice feature of this data, that you can look through the vegetation. So yeah, you get for each laser shot, you get multiple echoes or returns. So you can get several XYZ coordinates for each laser shot. And the results of these measurements are actually the plane positions. T is time, the timestamp, and then we have XYZ coordinates. And then you get for each reflection, the echoes or points, you get also the timestamp, the XYZ coordinates, and usually also an intensity value is recorded. That is the amount of light which is actually reflected. We will have a look. It looks more or less like a black and white photo, not like our visible inspection, because the laser usually is in near infrared. But so you have, but you have different gradients of gray for vegetation, streets, and stuff like that. So you can imagine that you get a lot of points. Actual scanner systems shooting 200,000 hertz. That is, you get 200,000 pulses per second. So up-to-date scanners will provide you up to, I say, 30 points per square meter. So this is a really new dimension of detail you get. And you get not only 2D information, but you get real 3D information. So we can have points that are exactly located at the same XY coordinate but have different Z coordinates. So this is something special to this data too, because in case you would like to convert it to a raster data set, you have to decide which point to use for your elevation value. Do you like to have something like a ground value, or do you like to have something like the top of the tree? You must decide, because in a raster you can only have one elevation. It's not really 3D, it's 2.5D. And we will have a look how to create classical products from ALS data today. And the typical products derived from such data are, first of all, a digital surface model. That is the overall top coordinates, including the trees, the buildings, all objects on the Earth's surface. Then we will create a digital terrain model where we remove all objects on top of the Earth's surface. That is, we remove trees. And what is more difficult, we also will remove buildings, because you see here, we will not get any ground points under buildings because they are solid objects. Vegetation can be penetrated by the laser beam, but solid objects, we get a gap in our ground model. We will see that we have to filter out these objects to remove them and have a gap in the data set, which can be interpolated later. And the third product, usually derived from such data, is a normalized digital surface model, which is simply the difference of both. We have the digital surface model describing the top surface. We filter out these objects, getting only the terrain, and subtracting both normalizes this model, and we get only the object heights. So the terrain is filtered out, and we know how high is a tree, how large is a building, and so on. We can directly, or we store actually the height of each object on the terrain surface. So, yeah, we will create all these three data sets now. First of all, you have the presentation, so this is just the listing of available modules for LiDAR processing. We will not use all of them today, but it should provide you an overview. So important is the import and export. So we have the possibility to read and write files in common LiDAR formats. So in most cases, these data is provided in LRS format, thus. This is a binary format, and we will have a look at it later. We will use it. Besides import and export, there are some conversion tools. We can convert the point cloud, the points, to grids or to shapefiles, and the other way around. We can use a normal grid or raster data set and create a point cloud from it, in case you would like to have the cell centers as point cloud, for example, which can be useful in some cases. So we have some conversion tools to support other data types. Then we have tools for the manipulation of the point clouds. There are some simple tools like a point cloud cutter, where you can cut out your area of interest, for example, by simply providing a shapefile with the boundary of your area of interest. Or you can do it interactively by selecting the extent in the map view. Then there's a module which can be used to thin out the point cloud. And this means that we are reducing the point density to get a smaller file, for example. Then we have a module to transform the point cloud. That is, we can shift it, rotate it, or scale it in case we have to adjust a little bit of the referencing. And we have the possibility in the SAGA point cloud format to have point cloud attributes to calculate, besides our coordinates and the intensity, to calculate further attributes. So we can imagine it as a large table. We have coordinates, and then we can add further attributes, and there's a module to remove these attributes again in case your data set is growing too much. And then we have analysis tools. For example, we can perform cluster analysis on point clouds to automatically group points, hopefully into useful classes. We have a point cloud attribute calculator, which is more or less the same as a grid calculator as you know it, but you don't work with different grid layers. You work with different attributes. You can, for each point, you have your attributes, and you can perform calculations on these and calculate new attributes.
So the cluster analysis for point cloud, it's for extract the feature or to aggregate point clouds that has the same.
Yeah, for example.
Extract feature.
There you can extract features, or you can calculate new ones. You can normalize an attribute. You can, for example, you remember we have return numbers, first return, second return. You can create a flag, which one is the last return. Simply, it will get clearer once we visualize the data. But yeah, you can create new attributes or recalculate others. And you can also perform conditional queries like if then else constructs on this with this point cloud calculator. Then we have a reclassifier or subset extractor. That is, you can reclassify an attribute or use it to extract points that have a specific attribute value. For example, all first returns. So we get a point cloud which only shows the first returns coming from the top. And we have a DTM filter, which we will use today, which not actually works on the point cloud directly, but on a grid data set which is derived from the point cloud and which can be used to filter out all cells which are not ground. That is, remaining buildings, vegetation artifacts, and stuff like that. We will see it. And finally, we have a 3D viewer for point clouds to visualize them in 3D, because you will see it's really a difference that you have true 3D data and not only 2.5D data. Okay, so this is just a quick overview about some of the possibilities to work with point clouds in SAGA. So, and yeah, first of all, I have provided you a LRS file. We will have to import this LRS file. I don't think we have the time to go into the details of this format, but you should know that it is more or less a container which can be used to store quite different information.
It's a binary format?
It's a binary format and has no ASCII or other meta information. So you don't see anything from the file itself. And you don't have any information which attributes are stored actually for each point. So the first step is we will use a module called LRS info, which will just read this binary file and print out information about it. How many points are in it, what is in its header, we will see which attributes are actually filled in and stuff like that. Okay, so let's switch to SAGA. You should have a module library called import export LRS. And when you open it, then you see that there's the LRS info module. And then as with other files too, just click into the field right to the parameter on the ellipsis button, and then you get the file dialog, and move to the folder data input, and there's a file called str23 clipped las. This is for strip, because usually LiDAR data is scanned from, well, in this case it's a helicopter flight, and they did many flight strips. And this is just a small sample from one strip. But you see we already have 144 megabytes. Also you will see it's only covering a small extent. So select it. Leave this unchecked, otherwise only the header would be read from the file, but we will get not all information we would like to see. So now, without checking this, the module will read the file completely and then will print out information about it. Simply execute it. Then you see it takes some time to read all the file. So, and now it's just make the message window a little bit bigger by taking this one up and scroll up. Then we get a header summary, file name, for example, which software was used to generate it. Then we get some information about the number of points, about the bounding box, and stuff like that. And most interesting are the minimum and maximum values reported for the attributes. If you scroll down, you see that the LRS format could store all of these parameters from time, that is GPS time, to return number, intensity, a flight line edge, that is those points who are at the edge of a flight line when the scanner has its maximum angle. It could be a classification could be stored if available for each point. So is it ground, is it tree, is it building, or stuff like that. And we could attach RGB color values to each point. And then we get a number of points per return listing. So we see we have about 4.7 million first returns, about 500,000 second returns, and so on. So the total point count is about 5.5 million points. Okay, so we see from the attributes which attributes are actually available. We see we have return numbers 1 to 4. We have intensity values from 3 to 1880. We have no scan direction flag, but we would have a scan angle rank, and so on. And this allows us to decide which attributes we actually import from this file. Because if you would select, for example, the flight line edge, we would get zeros for each point. So this is nonsense, and we can decide which attributes are useful for us. So this is done with the import LRS files module. You just select the same file as input. Oh, once again. So, and then you see just checkboxes for all the possibly available attributes. In our case, we will use GPS time and we will use intensity, just to show you two of these. The edge of flight line is not of interest for us at the moment. if you have made the settings, execute the module. And then you can switch to the data tab. And you should get a new data point cloud of type point cloud. And it's called like the file. So, and then you can do a double click again to visualize it in a map view. So this looks a little bit like a raster data set, but you can use the zoom tool and get in, and you will see that these are actually points. You see the scan lines.
It's a big data set, so don't play too much.
It should work, hopefully, with so this is some really cool data. I switch back to the
What are these lines going diagonally?
power lines.
Power lines, okay. It's not the arc spot, it's real.
It's real feature. It's a problem because we would like to, well, we have to remove it too for getting a terrain model. But we will see some interesting things now. I would like, we have, in the morning I showed you some of the settings for grid data sets, how to change colors and stuff like that. And I would like to show you some other settings that are necessary for point cloud data. So we have visualized it in a map view. And when you have a look at the settings, then we have typical settings like no data, which we also have for gridded data, transparency, which we used in the morning for overlays. But now we have a parameter which is called point size, which allows you to decide how big a point should be drawn in the map. And the most important is we have a parameter called value aggregation. And this parameter is controlling the order in which the points are drawn in the map, because the map is 2D. And each pixel can have a lot of points with different set coordinates. And this parameter lets you decide which one should be drawn. The lowest one, the highest one, the first one, the last one, and so on. And the other ones are similar to the grid attributes.
But it's these choices that make the difference to display the digital terrain on digital surface model.
Yeah, that's it. More or less, we get, if you try it, now we have displayed the highest set value. So you see the power line and you see vegetation and stuff like that. Just turn to the, or switch to the lowest set value. And if you apply it, you will see a lot of objects are already removed because it's a 3D data set. And now we view the lowest point recorded at a pixel location.
It's like the first and last pulse.
Yes, it's like first and last pulse. So
To select, I mean, when you import it, you could select if you want to import.
we will divide it now in the next steps to get this one and this one, because we need both. But you still see that there are artifacts, so you will see that there are still the buildings in it, and there are also vegetation rests, because not at all locations the laser beam could penetrate the vegetation and get a ground point. In some cases the vegetation was too dense and we have it in. But we had to extend the GUI to have this parameter in order to provide some possibility to deal with this true 3D data. Okay, this is how to visualize it in a map view like other data sets. You can overlay it with shapefiles, with grids and stuff like that. It's just a normal SAGA map. But as it's interesting to have it in 3D, we also implemented a point cloud viewer module, which allows to view it in 3D. It's different from the raster 3D viewer we had in the morning, because this is just rendering or draping something about a 2.5D surface. Now we need a viewer which is really 3D. So change to the modules tab and then scroll down. There are shapes, point clouds, and the shapes, point clouds viewer library, which actually contains only one module, the point cloud viewer. Select it, and now you can specify the point data set as input and execute it. This is my development version. So now I have my view on the wrong screen. I hopefully get it over. Yes. Get it not fully over. You can use the left mouse button to navigate. I think my development version has crashed. So I cannot show it to you. This is really a pity. Why? Okay. Why is that? This is, where is it? Gone. I try it again. Otherwise, I will have a look at some of your computers to. Ah, this is really. Try it again. So something. Maybe I try it this way. Okay, I got it working on my screen, but I don't know if I get it working here. No, sorry. So I have to look at some of your screens to explain it a little bit more. You can move it along. You see a lot of detail. You have a small window on the bottom left, which will allow you to select a small subset. So you will not have to use the whole extent. It's a little bit difficult to use the trackpad. It's easier with a mouse. But yeah, you can see for those who where the computer power is not really enough, you can use the level of detail slider to reduce the number of points drawn a little bit. Can go down.
This point cloud viewer, is it within SAGA or it's a, it's a separate application?
No, it's in SAGA.
Okay.
It's just that I don't get it on the beamer. I don't know. So I.
Guess what? My computer didn't.
So now you see it colored by elevation, but you can use the color attribute and change to intensity, for example. Then you will get something like a photo. Now only colored from blue to red. So you can go to the advanced settings. Maybe you have a look here. Ah, sorry, for sure. We forgot you. So,
I'm ready, but I'm missing the file.
yeah, okay. Yeah. Yeah, colors. This opens the palette editor, then presets, and then select grayscale.
Probably, well, I missed how you install it, but I have a SAGA version, that one, and I don't have the import class.
Ah, okay. Then I don't know where you. Is this? This is a pity. I save you the point cloud, so we get, or you, have you a stick, or something like that. Then I.
It doesn't interact with the design. It happens something here, nothing here.
You can. Can I have? Can simply select here a small rectangle. Then you have.
Okay. But here, why you didn't change the color scale or something?
I don't know. This looks interesting. You will change the palette, oh,
Yeah.
didn't you? Okay. So this is simply showing you height slices of set. So
Okay,
and
so
you
I
can,
select it.
yeah, and
here.
right mouse button zooms out to full extent.
Okay.
I will save you it as a SAGA point cloud, then you can load it directly.
Okay, but how could I have the module?
You need the liblas. It's a library which is used, and then if you have it installed on your machine and you compile SAGA, then it's automatically detected and the module is compiled. And if you have it as downloaded as a package, then your package maintainer build it without LAS support. So you maybe can ask him to provide a version with the LAS support.
But it's a bit heavy. It's a bit heavy.
Yeah, it's for sure. It's a lot of points.
If you will make it subset it, I mean, just a small.
We will.
Like 1,000 points is enough for exercise, right?
No, we will change to raster in a few minutes. I just wanted to show you. We will not touch the point cloud anymore then. So it's just to show you some detail which you won't see with any other data. So
What if you will change it in SAGA? You can save the working image, right? So you can put this temporary file, grid file catching or something. So maybe that gets faster.
yeah, we will convert it to a raster. I just need to kill my process. Or maybe someone other in the meantime can save the data set by a right click and copy it in here, and we can distribute it. Just close the viewer to save the data set with a right click, and that would be nice. So because but you can still keep the viewer open, the others. So, in case you visualize it with a grayscale palette, the intensity, it really looks like a photo, more or less. Right? So this is interesting possibility. The problem is that the intensity depends on the length of the laser beam. That is, in nadir position, you have the highest intensity values, and it's getting darker once the scanner gets to the edge of the flight strip. And the next step would be to overlay or merge several flight steps, and then you get inhomogeneities and the intensity values. So you would need to normalize these values before you can use them. The other thing, oh, I forgot. Yeah, it's we have forgotten to import the return number. You could, in case you like to view it, you have to re-import it. Yeah, I have forgot to set the flag, the return number, which would allow you to see that we have first returns on top of the trees and higher return numbers up to the ground. But that would be just another possibility to visualize things. If you go back or visualize by GPS time, then you can see the direction in which the helicopter has been flying. Simply color by GPS time, and then you can see the flight direction. So you see in this case, excuse me? Yeah, because I cannot show it you in 3D. In 2D it's not so interesting, but you would have to use the number of the return. And in case you like to calculate the last return, you should also use the number of returns of given pulse, which shows for each return how much returns were recorded with this pulse. So we have, for example, 2 returns. Then you have a return number of 1 for one point and a return number of 2 for the second point. And the number of returns were 2 for both cases. So we have 1 of 2 and 2 of 2. And this allows you to detect last returns. Okay.
We save as a grid, export.
No, just do a right click on the data set. But you go to data. And then on the data set itself, right click and save as. So, and then you, yeah, it's all right. You have a different paths. There's some backslash missing, I think. So. Have you save as? This will save it as Saga point cloud. It's okay, so you can save it.
But why? We already have it, no?
Yes, but it's in RAM, and this would allow you to save it as Saga point cloud, so you can simply go to File, Load point cloud, and you don't need to import it from LLS. Did you manage to import the data? Parameter file. You need to provide here, select it, and then execute. So, okay. So, okay. So there would be a lot of other interesting things too, but you can explore this file yourself. You should be able to load it now, did you? Okay. Yeah, copied it. Great. So you can simply go to File menu, Load point cloud, and load this data set. So you have it too. Yeah, so you have just to You must copy it from here. Yeah.
I think
Yeah, but it's a native format. Now you can load Saga point cloud. You don't need LUS.
Oh, okay. Thank you.
And it's, I don't know in which folder. I think, did you put in the input?
The course slider.
Core slider, okay.
I need to.
I don't know.
Maybe this one.
Yeah, genau. Just get this one or both. This is a meter file, but and then you can load it, and we can start working with us. Okay, so I think now everybody should have at least the data set. I have recovered too. So, first return, last return. So we have our 3D visualization. And now we will start to generate a digital surface model. We will start with the easy one, the surface. Wo ist es? Good. Okay, so in order to get a gridded digital surface model, we are using the point cloud to grid module by simply aggregating the highest set coordinate found in each grid cell. So the module does nothing other than looking for each grid cell, looking which points fall into this grid cell and which one is the highest. So you find this module in Shapes Point Cloud Tools. If you scroll down. And there's a Point Cloud to Grid module where we simply specify the data set and we aggregate not the first value, which is found for each grid cell, but we aggregate the highest set value. Then we have to decide on a cell size. In this case, we can keep 1 meter. Apply and execute.
Shouldn't it be the same for the first value or the highest?
No, it's not the same. It's the first or the last value is more or less random, in case the points are not sorted in some by something like GPS time. It's just the order in which the points are read in. So it's of very limited use. Usually you would use highest or lowest set. So then some parameter is missing. You need to specify the point. First of all, okay?
Okay, yeah.
Okay. So when the module has finished and you change to the data tab, then you see 2 data sets, 2 new data sets. You can visualize the first one, which is called clipped set. So it's a little bit more pregnant than the point cloud, but you still see it's more or less the elevation. And for interest, you can also visualize the second one, points per cell, added to a map. This is the point density, how many points were found in each grid cell. And you see all these stripes. This is because the helicopter was not very stable and some parts got scanned more times because the helicopter grew up, scanned in the front, corrected and scanned to the back, and then you get these higher density stripes. And you also see that there's some, there must have been some wind because the axis of the flight strip is in this direction, but the helicopter has slided a little bit to keep on track.
The cell sites one data were based on local projection, no? Because they were not projected. The projection of point clouds, it's based on local system aircraft, no?
Yeah, first of all it was, but the data then was projected.
Because
Yeah.
just maybe you didn't understand the system of projection, because in the description was nothing.
No, it has been a projection.
So
It's
one, it refers to 1 meters, 1 cell size resolution of this grid.
I don't.
One,
It's one. Yeah, we have a
cell size,
we have a resolution of 1 meter now.
1 meter.
Yeah.
And how it makes the average of the 10 or 20 points that were in the sex?
In this grid,
Yeah.
it's just the number of
I
points.
know in the other.
In the other one, it took the highest point.
Yeah.
The highest point. So, change to the map. There you can disable this data set by double clicking on it simply. So it's just turned off. We don't need it currently, just by a double click in the Maps tab. You could also remove it by a right click, close, then it is removed from the map. Okay, so we don't see much, but you know the analytical hill shading from this morning module. Just calculate a shading. It's in the terrain analysis lighting module library. Go there and calculate an analytical hill shading. Specify the set data set as input. Got it?
I lost the map.
So we don't see anything.
No?
Maybe
And these are wrong. So,
maybe we
are you working on the grid or on the cloud?
on the grid. As soon to full extent.
Yeah, wait, but the grid is wrong.
Why?
Because it was not finished when I opened it. Oh, man.
This seems to be empty. Huh? Number of columns already, number of cells minimum. No, it looks right. Why don't we see it? Let's make a new map. Maybe you have several map views. So.
See that's
Okay. It's not finished yet, yes.
No, it must be.
Have you stopped the module by X?
No.
Let's try it again. It will be overwritten, get overwritten. Get clipped. This is crazy. What is here?
See?
No.
My whole week goes like this.
This one is right. So
When that's
maybe you didn't use the first one, close the second one. So we use definitely the right one in the module, and you see you did use, I don't know how you created it, the second one, maybe, and now we should also get a full grid. So.
anyway.
Huh? We will get it because it's just that we created a new data set. These ones are all wrong because they are too small. Yes. Remove them. And now we have this one in a new map view, and it's how it should be. And now we calculate the shading. So it's just as we did it this morning. So, okay, once you have calculated the shading, you can overlay it. I didn't calculate it already. And, for example, change the transparency to 40%. Okay. What we have missed, but we are a little bit in a hurry to finish up, is to close some gaps. We had some gaps in the data set, which we will fill. We will do it with the ground data set, but it's on the slides, so you can have a look there. It's just closing gaps, which we didn't do here. So finally, we should all have more or less this product, a nice digital surface model with all objects on the Earth's surface included. Okay, then next step would be maybe to rename datasets and save datasets just to keep a little bit of order in our data. So you could rename it, just change to the data tab, select the data set, and click on its name, and for example, call it DSM. So we can rename the analytical hill shading to DSM shade, for example. Okay, you need always to apply these changes to make them permanent. Okay, so next step is to create the terrain model. And we will start again with the gridding of points, point cloud to grid, but we will use the lowest set method now. That is, the lowest point per cell will get gridded. Point cloud to grid. The input data set stays the same, but now we aggregate the lowest set value. When this has been finished, you can have another one, script clipped set data set. That is why we have renamed the other one. Add it to a new map view. And then you see something which is quite similar, or similar to that which we achieved in the GUI by just changing the drawing order. But we have some buildings in here, and we have some vegetation in here. To make it, or for the next steps, we will now close the gaps. We have some no data gaps in here. We will use a very simple module for that. You can scroll up to grid tools and use the close gaps module. And in this case, specify the grid system, and now the script clipped set data set. And in case you don't set the change grid to create, your data set will be overwritten. So the input data set will be filled and no new data set will be created. This is fine with us. So just provide your new lowest set grid and execute the module. You will see some animation how the interpolation is done. And then we will have a data set which has all gaps filled. At the moment, we don't care about the borders. We could mask them later on. So we will continue. So in order to see what we are doing in the next step, calculate a hill shading for this data set too and lay it on top of this one. So we again use, there, can you show you, if you use modules, menu, you see at the bottom, you see the last modules you used. So in case you don't like to scroll a lot, simply go to the analytical hill shading, which is listed here because we used it. Provide the script clip set data set, and now set it the output data set to create. Otherwise, our previous data set would be overwritten. So just provide these two parameters, okay? And then we overlay it. We don't need to make it transparent because I will show you, I would like to show you some of the problems later. So now we see that we have still a lot of vegetation. We have still buildings for sure, but the power line, for example, is already removed. So, and now comes the magic to remove these remaining objects from the surface, for which we will use the grid filter. So we have closed it, we have calculated the shading, and this is more or less our result. So now we will use this DTM filter. And just a few words. It is assumed that a higher cell, well, the probability that a higher cell could be a ground cell increases with larger distance between two cells. So the filter defines a height difference which is acceptable between two cells as a function of the distance between the two cells. We have a filter kernel which is centered at a grid cell. We define a radius of it's more or less a moving window. It's not a 3 by 3 moving window, but we define a radius. It's a round window. And we define a slope of this cone. How steep is it? Is it smaller? Is it wider? And it is placed on each grid cell, and it shows us the maximum allowed height difference to the neighboring pixels in this window. And in case any of the neighboring cells in this window exceeds this allowed height difference, we will remove this point because it's not ground. So it's a little bit complicated, but it's more or less a simple filter to do ground, non-ground filtering. And we can control which objects are removed by defining a filter kernel radius and by defining the slope. The slope decides the increments of the allowed height differences. So we have two controls. Terrain slope, which should be approximate the slope of the filter should be approximated by the terrain slope, and the radius of this kernel. And that it's logical that we must choose a radius that is at least half of the size of an object we would like to remove. Because if you imagine a building, which is a solid block, and we examine a cell on the building, then the filter must be able to reach a ground cell near the object, near the building. So our radius must be large enough to reach a ground cell. So in case you have very large buildings, it's getting complicated because you would have to need to use a very large radius. So more or less, it's always a trade-off. Both parameters influence the filtering result. You can have commission and omission errors. Sometimes you filter away ground cells, but you don't like, and sometimes you keep cells which are not ground because, for example, the building is too large and cannot fit into the filter. So it's always a trade-off, and it's quite difficult to find a global setting. So often there are different filter settings used for urban areas, for rural landscapes, for mountain areas, and so on, because it's impossible to find a filter setting which works everywhere. And because we have not so much time left, I would assume you first run it with my values. I optimized in 3 or 4 iterations by running the filter again and again. It's easy in SAGA because you just need to change the values and the grids are overwritten automatically, and you just iterate until you get a good result. So let's go to grid filter and DTM filter. I have to scroll up. Grid filter and the DTM filter. Here we specify again our script set data set, which are the lowest coordinates per cell. And we will create 2 complementary grids, one bare earth and one with the removed objects. So we had a search radius of 10 meters because we have quite large buildings and we have quite dense vegetation where we have no ground points either. And we have a steep valley, so we have approximate terrain slope of 75%. Have I used a confidence interval? I don't think so. Oh, yeah. The confidence interval is a further parameter which includes the standard deviation within the filter radius to remove outliers from the maximum height calculation. So we can use this confidence interval. It's calculated from the distribution, but I would have to have a look at the paper again. I don't remember how it was done exactly, but the paper is given in the description tab if you have interest to get more details. So then execute the module. Processing time depends on your radius, because now we have to investigate for each cell a moving window of 20 cells, 2 times the radius. So it's a 20 by 20 window which is moved over the grid. And once the module succeeded, you will have 2 new data sets. And now visualize the bare earth data set on top of the hillshade. And then we will see which of the objects were removed. We can see we have removed the vegetation, we have removed buildings, and the other ones are ground. So because we look through the gaps of our bare earth model. In case you like to try one thing, for example, you will recognize that some of the buildings haven't removed completely because they are too big. In case I would, for example, say, okay, I relax the terrain slope parameter and go to, say, 50%, then you can immediately see what has changed, because once it has finished calculation, the view will update, and you will see that we remove too much terrain points. It will have finished soon. So now you see, oh, we got a lot of more gaps. We have completely removed stripes or strips of ground cells. and this is not what we are expecting. So I turn back to the original values. Okay, so this is something you can play around with. Depending on your data set, this will always vary, these parameters. Okay, so next step, this is the result. We have removed non-ground cells. Next step is to close these gaps because we want a continuous terrain model. So this could be done with several modules. A nice one is the multi-level B-spline interpolation. It's in the grid gridding library and, in the grid spline interpolation library. There you have a multi-level B-spline interpolation from grid module, which we will use. And grid spline interpolation, multi-level B-spline interpolation from grid. And we can simply provide our bare earth dataset. As target grid, we will use a grid. That is, we can set the extent by the grid system of the grids we already have for the interpolation. So the system will not change. And in case you like to follow the interpolation process, you can click on Update View, which will show how the multi-level interpolation works. Simply execute, and then a new dialog will pop up which asks you which grid system should be used as target. So to which extent we would like to interpolate. Select our 1 meter. We have only one meter grid system, and press OK. And then you can follow the interpolation. So it's coarse and gets finer and finer and finer. This is determined by the threshold error and the maximum level. So you can see always the error reported and until it fulfills these criteria. Okay, so this is our final digital terrain model. You could use the analytical hill shading module to get a nice view by simply providing our bare earth multi-level object and create a new shading. This will also reveal that we have not removed all objects, that there are errors in the data set. It's not perfect. We will see this. Just add it to the view and set the transparency to 40%. Then we will see that we still have some artifacts. And also we have a noise on the fields because there's grass and stuff. So we cannot use this one for example, hydrologic analysis because it's too noisy. And in this case, it's nice to use a very cool filter in SAGA. It's called, in grid filter, it's called multi-direction Lie filter. This is an edge preserving filter, which determines the variance in different directions, grid directions, and adjusts the filter kernel to preserve the edge and just filter in the other directions. So we get the edges preserved, but we get a very smooth terrain model. And they just have to look at the parameters because we are running out of time. So we will use estimated noise of 2 and given relative. Okay. So provide your bare earth multi-level grid. It will create a new one, and we use a relative noise of 2 meters, and this is, I think, the default value is correct given relative. Provide that. This filter was originally developed for filtering SRTM data, which sometimes has elevation strip noise. So, and then you can go back to the hill shading module and simply change from the bare earth multi-level to the bare earth multi-level B-spline Lee filter grid and override the other hill shading. And then you see we get a very smooth, nice terrain model. Okay, so the last product would be the normalized digital elevation model, and this is simply the difference between these two data sets. And you can go to the grid calculus library, and there's a grid difference module, and yeah, just specify the DSM and the last bare earth multi-level B-spline from grid Lee filter, and then you will create a difference grid, and you have a look at it, then it is now made plain. The terrain is removed. The difference grid uses a different color palette. You can simply choose it, change it by choosing the default one. So you can get a picture like you are used to. So you see we have very high trees, lower trees, and stuff like that. So we can do a last computation of a shading for this data set, creating a new shading from the difference grid. Create. So, and overlay 40%. And once you look at this one with the raster 3D viewer, you see it's all plain, and we have only you must need select as elevation the difference grid, the NDSM, and increase the resolution to 1000, for example. And then you see we have a completely plain model where each cell just represents the height of each object on top of the Earth surface.
So that will be the tree heights or something?
Yeah, this is tree heights, for example. For vegetation analysis, you could make a mask for vegetation and would have tree heights, for example.
You can compute it in value without volume.
Yeah, you could use, next step would be to create a vegetation mask, just masking everything to no data and vegetation. And the vegetation should keep its elevation. And then you go to the segmentation module, imagery segmentation, watershed segmentation, put this grid into it, and you get individual trees derived. So it detects local maxima, which should be the treetop, and segmentizes like a watershed, and you get the extent of the individual trees. So I can show you. I have done this with another data set. Where is my mouse pointer?
But still with a lot of noise, because some trees, they will be so close together that you won't be able to distinguish them.
Yeah, it's
Depends. In a natural forest, maybe it becomes difficult, but if you have an artificial forest, like a planted one, then it's easier maybe.
Yeah, I can show you an example I have calculated last week for Switzerland. This is just height colored by grayscale. So these are buildings, large buildings. And this is what we derived with this approach. The rings demonstrate the radius, the determined radius of each tree. So this is just 3 computations from where we are actually now.
Each ring is one tree.
The segmentation searches for a local maxima, and then it lets more or less flow water from this maxima until it detects the next tree. So then we get segment IDs, object IDs for each tree. And this grid can then be used to calculate something like radius. Tree height is stored in the grid.
And you can export as a vector file.
So yeah, this is another application. So you can do a lot of interesting things.
You just need to have the data fly.
You need to have the data, yeah.
Once you have the data.
But yeah, we have customers which now do it every year. For example, the city of Basel is flying every year because it's cheaper than doing all these possible measurements by hand, because they have a tree cadastre, they have building models of the city, they do all the street planning, they even use mobile laser scanning to scan all the streets. They use helicopter for airborne, and they use sonar for the Rhine river. So they have a complete 3D model, point cloud model of their city. It's totally crazy. If you draw a profile through the city, you see tunnels, you see the city, you get the ground of the river Rhine. It's crazy, but yeah, it's a matter of money.
It's where? In which city?
Basel, in Switzerland. Yeah, you can have a look. I think they have a very nice web interface where you can view this data. I don't know if it's public accessible, but they said, yeah. But in the last years, the prices dropped for such things. I think you get 1 square kilometers for about €100. It's not that cheap as making orthophotos or something like that, but it's getting cheaper and cheaper. Okay, so hopefully I've shown you some interesting aspects which you can do with SAGA. It was a very small portion of all the possibilities. So in case you have interest to explore it more, have a look at the homepage. There are references to research papers and stuff like that, what is possible with SAGA. And yeah, hopefully you enjoyed the session.
I will also, in the afternoon, I will just give you quickly, before I start with PlotKML,
Yeah.
I'll just show our SAGA, how you can link. So you can send from our operations to SAGA and get things back. So, and I actually, in PlotKML, I mimic lots of, I mimic the color palettes and some things, so you will recognize some SAGA screens in Google Earth. So.
Okay.
Thank you, Volker. That was very
Okay.
good.
Thanks.
It's not possible that we could be expecting on Friday.
Based on the load, so I'm looking at the load. So
I'm leaving tomorrow morning, so Tomislav will make a SAGA session. So
And it could be in case the laser scanner is on the ground. the structure of the file is also .las, or they generate different structure file?
In the meantime, more and more data is stored in the LIS format,
Okay,
but
also in the
terrestrial laser scanner is usually simply ASCII.
okay.
So you get ASCII file with XYZ columns, and then you convert it from there. You can import it from there too. But the LIS format is getting more and more prominent. There are a nice set of free tools, LAS tools, LIS tools from Martin Isenburg. These are command line tools for processing LIS files. We can also do merging, tiling, and stuff like that. So if you get to this data, have a look at this. And yeah, they are looking for some new formats for TLS data. Maybe it will make an extension of the HDF format, but we will see. Mostly it's ASCII. Okay, so I don't know, maybe Markus will do something finish something from yesterday or show.
He also wants to finish something.
Yeah, he told us that we should mention it, that he will use the lunch break to.
Is it lunch break or after the lunch break?
Or after lunch break, I don't know, yeah.
Yeah.
After the lunch break. Okay.
Okay, thank you.
Thanks.